This is my new module, Euclid Plus. It is currently controlling the clave or rimshot sound within this generative patch. The module operates synchronously or asynchronously, with the status shown on the sync LED. When in synchronous mode, Euclid Plus can play a Euclidean rhythm. I'm sure most of you are already aware of Euclidean rhythms, and there are lots of synth DIY routes to get Euclidean patterns into your system. Many, for example, will know Hagiwo-san's excellent 6-channel DIY design. I've had my version of that module running in my system for, I think, 18 months now. And I've used Tom Whitwell's code for the Arduino in several of my own modules which generate Euclidean rhythms, most notably the Euclidean Sequencer, which you've already heard in this video. Those and all other instances of the generation of Euclidean rhythms of which I'm aware are the result of algorithms running on microcontrollers. But Euclid Plus is different. It's just an electronic hardware circuit, and that gives it some interesting properties, which we'll look at now. The Euclid Plus module has two main subsystems. On the left-hand side, as you look at the front panel, is a clock divider, and on the right-hand side is an internal oscillator. If I apply a clock signal to the clock input, then that clock signal is divided by a divisor which is set by the divide control and displayed on these LEDs, but the divisor is 1 minus the number displayed on the LEDs. And perhaps perversely, the least significant bit of this binary display is on the left hand side. So at the moment it's set to 2 in binary, and 2 minus 1 of course is 1, so it's divided by 1, it's just the clock signal. If I increase that to say 3 there, then 3 minus 1 of course is 2, so the clock is divided by 2, and so from the divide output you get the clock divided by 2, which you now should see on the oscilloscope screen. If I increase it to 4, then 4 minus 1 is 3, the clock is now divided by 3. If I go up to more useful numbers like there, 9 minus 1 of course is 8, and so now we have the clock divided by 8, and in fact it will go all the way up to 30. I can set it to 31 if all the bits are illuminated, and that just about shows on the screen once it's triggered and stabilized, which is why I set the screen up in that way. I'll come back to the 8 setting to show you some more effects of the other side of Euclid Plus, which is the oscillator. Okay, we're now going to look at the oscillator on the right hand side of the module. The clock divider is set to division by 8, which you can see on the oscilloscope. I'm going to connect the mult output, short for multiply, of the module to the third trace on the oscilloscope screen. You can now see that it's producing a square wave output, You can also see that that square wave is asynchronous to the clock and the division. The trace is wandering around. I can adjust the frequency of that square wave either upward or downward continuously with this frequency control, also with an external CV input and an attenuverter on that input. And importantly, to the operation of Euclid Plus, there is a sync control, both a toggling push button and an external CV input, which allows me to generate some hard sync inputs to this oscillator from the clock divider. And if I activate the synchronous mode by toggling this sync status with a push on the push button, you'll see now that we're generating sync inputs to the oscillator such that the oscillator now static relative to the clock and the divide signal. If I increase the frequency, you can see that although the frequency of the internal oscillator increases, it no longer wanders around. It's stabilized by this syncing, this hard syncing process. And that's central to the operation of the rhythm generator inside Euclid Plus, which I shall demonstrate to you next. Okay, I now have the same divide by 8 setting on the clock divider, a slightly different setting on the oscillator for interest, and I'm going to plug a 4th channel of the oscilloscope into the rhythm output. The system's in synchronous mode, and you can see on the oscilloscope that the output is steady. It's producing 3 pulses per 8 beats of the clock. And if I swap the oscilloscope channel that was looking at the oscillator output for what is called the comp, short for complement output, you'll see that the complement output is asserted on those clock pulses where the rhythm output is not asserted, so it in that sense is the complement of the rhythm output. So whenever the rhythm output is not triggered, the complement output is. You have a fixed pattern therefore generated on every cycle of this 8 pulse repeating pattern. If I take the system out of synchronous mode, it won't be any longer repeating, it will move around with the same kind of number of onsets per 8 pulses, because that's really determined by the frequency of the oscillator, and the same kind of feel if you were to listen to it rather than look at it on the scope, the same kind of number of onsets giving it the same density, but it changes every bar. Usually is that length in musical terms. It moves, it evolves, and that makes it interesting. If I synchronize again after a bar or two, it stabilizes. That's what this module Euclid Plus rather is all about. It's about generating patterns, amongst which are Euclidean rhythms for all sorts of different repeat lengths and all sorts of different patterns, because if I change the frequency, as you'll see, the pattern changes. And if I've demonstrated already, take our sync, the pattern changes dramatically and continually. If I do the 2 things, you get almost endless generation of different sequences. Here Euclid Plus is generating a fixed Euclidean rhythm which is associated with the Tresillo or Habanera pattern. I'll put Euclid Plus's sync under the control of the rest of the patch to allow the rhythm to move on from that Tresillo pattern and evolve into something different, and use that to play out from this video. Thanks for watching.